part 1, we gave you a little background and information on the WQEE. Now we will have a look at an example site, and I'll show you how to enter it into the WQEE app. So please grab your iPad, open up FileMaker Go, make sure you have the latest app and reference materials installed on your iPad, and follow along. So let's use this site to do an example assessment. The first thing I'll do, bear with my artistic abilities, is I'll show you, you would stand on the bridge here and look downstream. For convention, we look downstream and say anything on our left is the left-hand side and anything on the right is our right-hand side. We are looking for anything disturbed by humans when constructing the road and what is the extent of each component, how much erosion can we expect from each component, and how much of that sediment is actually reaching the creek. So start by pouring your imaginary buckets of water and see where the water will run over your site and components. All the arrows heading towards the stream will be grouped together as a mini catchment. So the water will run down the road here, both sides of the road. We'll come down here through the slope and run down into the creek this way. In this example, we have an old cut bank. As you can see, this old cut bank has completely revegetated. So although we have one of about 2 by 8 meters, we can say that the size of the cut bank is about 16 square meters, but the erodibility of it is still 0 because it's completely revegetated. And so it's no longer prone to erosion. But we'll highlight it anyway. So that would be your cut bank component. The components we are concerned with at this site is the right road surface and left road surface. For this right road surface, we'll outline it here for you. And just for your interest, we'll outline the left road surface as well. So for the right road surface, we'll say it's about 50 meters long and 5 meters wide. We want to characterize the normal traffic on this road over the coming year. Here, they are presently harvesting 2 blocks above the bridge, so we will say that it is at least a moderately used road. The slope is 4% on the right road surface and 7% on this left road surface. The road surfacing material is average for sediment generation. Inputting that data, we will come up with a rate of erosion for this road of 2 millimeters. This means we'd expect over the period of 1 year for 2 millimeters of fine material to be sucked out of the road and run toward the ditch. You may have experienced on your recon of your road network in the spring that a steep road grade may have degraded into rubble because all the fines have been washed out by winter rains and or snow melt. Depending on the steepness of the slope, you come up with a reasonable estimate of how much sediment is being generated. Now, keep this site in mind, and we'll go into the app and I'll show you how to enter the information. So open FileMaker Go, and then find your WQEE field and make sure you open the most recent one. So I just want to show you, there are many training materials embedded within the app to help you understand how to conduct the water quality evaluations. So I'm just going to take a screenshot so I can highlight them for you. Here, you can read the original protocol manual itself and upgrade your understanding of the FileMaker Go app and review all training presentations as delivered. Or over here, you can look at pre-made YouTube videos on specific topics of potential interest. Please spend time looking at what's available in the references, as they can be very useful out in the field or at home if you need a refresher. The WQE app provides the means to sort and manage your data. We can do all sorts of manipulations, including sorting for districts, states, amounts of sediment, licensees, and many other characteristics. It's quite a powerful tool for watershed management issues. Now, I'll run through how I'd enter the data from our site assessment that we did for an example. If this is the first site associated with a specific transect you want to evaluate, hit the new opening icon on the top right. It'll prompt you to enter the evaluator ID. Hit OK to continue. Next, enter which district you are in. We'll hit Chilliwack for our example. You need to enter your evaluated by box. I'll put in mine, but make sure you put in yours. Next, input the proper ID for that opening. If the app rejects the ID you've just entered, that means it is not on the FREP random list for that year. If you are sure it is the number or name you wish to enter, you can change opening ID to other ID within the app, and it will allow you to enter any string of letters or numbers you wish. We will enter 1, 2, 3, 4, 5, test. For your second site within any given transect, you merely click on the New Site button up here on the top right. Consecutive numbers will appear, 2, 3, 4, and so on. So let's return to sample site ID 1 and complete our example assessment. Now, while standing over the bridge or culvert, click on the GPS located on the top left under the Location tab to generate your location automatically. Once the satellite location has been received, you can speed up the process by sliding the Slide to Cancel bar twice to speed it up a bit. Now, see if you can guess where in the world I am given the coordinates. Give yourself a bonus mark if you get it. Later, you'll be able to create a KML file of this location that also contains the rating you gave the site along with some other information so that you'll be able to easily produce a map of site ratings like we looked at earlier. You then fill in the description fields, things like your permit holder, your road surface, material quality. For this specific example, remember we determined the road surface materials were of average quality and the road use was moderate. Let's say that there is an intake downstream from this site. So click that one. And the distance to the intake is 8 kilometers. The site was serviced by a bridge, and that was 7 kilometers long. Sorry, 7 meters. And it was a stream crossing. So you have lots of options to fill in here. Take a look around your site and see what fits. So when you hit that that stream crossing bar, it'll bring you over to the next tab, which is the Components tab. So here we are going to enter the components of the site. If you remember on our site, we had the road surfaces and the cut banks. You can see all the options in this drop-down menu. First, we'll enter our road surface. So select road surface, and if you'll remember, we'll do the right road surface first. It's neither upslope or downslope, so we'll leave that one clear. Now, the connectivity is as discussed. All the water was flowing to the bridge and into the stream, so we select all or one. Next, we select the portion of fines in the material. For active road surfaces, it is always 1. It's all fine sediment being generated. Normally that will automatically be populated for you. For cut banks, you'd have a portion being coarser materials, but with roads, it'll always be all or 1. If you do want to record coarser material movement, it means you actually have a gully forming, and that would be treated using the next tab, the mass wasting tab. I'll show you that in a moment. So we'll hit all, and that'll bring us to the next part of the Components tab. Now, on the left, you can see we're still the RRS stands for the right road surface component we're entering, and it's asking us for the length and the width. So if you remember, it was 50 meters long and 5 meters wide. And that will calculate the area of 250 square meters. Next, we'll say that the whole surface was erodible. And in this next column 9, it's asking us for the slope, which was 4%. The road use is moderate. And the road surface quality is average. You can see here that you only need to fill in the yellow highlighted fields. The rest are answers to calculations that the app completes for you. Here you can see that 0.5 cubic meters of sediment is generated from this component over 1 year. So let's enter the cut bank component just to show you how to enter it. What you do first is you hit this icon down on the bottom left of new component, hit that, and it'll bring you to the next line back in the first components tab. So open up the drop-down box, and for cut banks, we'll use this road cutbacks in the app. It was on the right-hand side and on the downslope. We'll say the connectivity is one or all, but just to show you, there's another option here. You can use these columns that are highlighted in green at the top to refine your connectivity if it isn't straightforward. In the first column, you enter the distance over the forest floor between the ditch outlet and the wetted width of the stream. We'll say here it's 7 meters, just for an example. And the next column, you enter the approximate area of disturbed drainage area upslope of the storm drainage outfall. We'll say for our example, it was 20 square meters. This will calculate the connectivity percentage for you. And as you can see, it says no connectivity. This is, if you'll remember back in part 1, we looked at the table that this is just finding the number in that table for you. Here, we've observed that the cut bank material was till and the portions of fines is 0.5 or half. So select that from this, and then I'll bring you over to the next tab where you can see that it's asking us now for the dimensions of the cut bank. Let's say it's 10 meters by 2 meters. And next you need to say the portion that's erodible, which if you'll remember, it was completely vegetated, so none of it is erodible. You are entering the information that you have a cut bank, but because the road is well established and the cut bank's totally revegetated, there is no erosion occurring on it. Okay, so next we'll go up, I'll show you this mass wasting tab. If there was mass wasting, you would fill it in this tab. If, for example, there was a slump near the bridge surface, you'd select fill slopes. So let's do that just so we can show you how it goes. The portion of fine sediment in the erodible material would be a little, 0.2. And let's say it was 1 cubic meter. And all of that went into the creek. This will calculate the amount of fines that get into the creek from that, which is 1 times 0.2, which equals 0.2 cubic meters. Another value generated from this mass wasting component will be 0.8 cubic meters of coarse material, which will show up later in our summary tab. The coarse material is generally of no consequence for water quality, but can have serious negative impact on fisheries values downstream, like pool infilling. So next, let's open the Stream Characteristics tab. This requires the evaluator to estimate the stream width and depth at bank full capacity, the stream gradient, and the roughness of the stream channel. Under this tab, you'll fill in the yellow highlighted fields, and the white fields will return certain calculations for you. We'll go down the list starting in the upper left-hand side and fill in the yellow fields. The estimated discharge in this case is at the time of visit, what is the flow and grade of your stream? Now, if you are evaluating in the summer, it may be completely dry, or if it's in the fall during a heavy rainstorm, you may have a peak flow. Here, we just want to get an idea of the nature and importance of the stream. Most of the evaluations are done in the summer when it is hot, and many streams have no water in them at the time of evaluation. It's good to know that. The more important streams obviously have water flowing year-round, and less important streams may only have water during spring runoff ending in late May. Consequently, when we call a stream S6, which is the lowest class stream, it should depend on how much water is flowing in the stream and not just how wide that stream is and the channel is. So this is why we ask you to enter the estimated discharge at the time of your visit. We'll enter 100 liters per second for our example. In this table, we are calculating what the discharge will be during a normal storm event in the winter season or spring runoff. So we need to enter the bank full capacity. How wide is that stream when it is flowing at that rate? For this site, we'll enter the bank full capacity to be 6 meters. And we will estimate the depth of the water at bank full capacity to be 0.3 meters. The channel gradient is 3%, which is calculated from you standing in the stream bed, looking upstream or downstream, what would be the average gradient of that stream. And finally, the roughness of the stream under Manning's coefficient. How much does that stream channel inhibit flow? If it was a smooth concrete sluiceway, it'd be a low number. Or if it's heavy brush or something that makes the water's pathway more tortuous, then the Manning's coefficient of roughness would increase dramatically. We'll choose cobbles or 0.04 for our site. Then we're asked if this is a fish stream. If it is a fish stream, then it's important to do an assessment of how it's impacting fish. You can choose yes, no, or you aren't certain. If you aren't certain, say you don't know, and then it'll be put into the evaluation and be part of the classification, even though there may or may not be fish in it. We'll enter don't know. On the right column, you'll see the velocity of the stream has been calculated for you at just under 2 meters per second. The Manning's formula will calculate discharge at a storm event for you, which in this case is just over 3 cubic meters per second. The next field shows the volume of sediment from the water quality protocol, that number we get from the combination of what was the surface flow, in this case 0.5 cubic meters, and added to how much fine sediment was additional from mass wasting, which was at 0.2 cubic meters. And so the app calculates the total to be 0.7 cubic meters of fine sediment. What we are saying is sedimentation is occurring over the average 10-day period. We see in this case that the change in turbidity of that stream would be on the order of 0.20 NTU, which is actually a small amount, and in this case, there would be no effect on fish. If instead we knew for certain there were no fish in that stream, we would choose that option, and then the effect would be changed to undefined. And that means there is no classification made because in fact there are no fish in that specific stream. Obviously there are many streams where you don't know whether it has fish or not, so you just revert to entering don't know. Many licensees classify S6 streams as fish streams, as it is very expensive to prove that they are not fish streams. Next, we'll have a look at this range tab across the top. The reason we do this range section is that the Ministry of Forests does have some responsibility for the management of livestock in range lands. These range leases are obtained through the Ministry of Forests. The issue with cattle is not so much concern of fine sediment generation, but with fecal coliform contamination. Now, fecal coliform and fine sediment are quite different. Fecal coliform can cause a number of diseases, Giardia, Cryptosporidium, and some types of E. coli, for example, and these can be very serious, especially for immunocompromised people. For our evaluation, if we have a site that we know has a drinking water intake downstream, plus on site we recognize the presence of livestock, then we do the range assessment. Otherwise, it is left blank. By and large, the need for this assessment is restricted to a few districts in BC, for instance, the Okanagan district, which has high livestock numbers and drinking water intakes downstream. In contrast, in the Chilcotin, there's high livestock, but low density numbers in drinking water intakes. In spite of high livestock numbers, it will not have this part of the assessment done because the stream is not used for drinking water. So across the top, you'll see there are subcategory tabs that consider plant community, ground surface, stream, bank, and channel, presence of livestock, dung, and range management practices. Observed conditions are noted for all subcategories. For example, under plant community, we could choose that the riparian vegetation is absent due to grazing by tramping or tramping by livestock, if that's what we saw at the site. Underground surface, if there's bare soil showing, check that off for your site. Pugging, meaning animal hoof prints right in the mud of the stream, suggests that cattle are in the stream and causing disturbance. Within the stream bank itself, there could be erosion due to livestock use. Lots of algae generally means lots of phosphorus and nitrogen have been increased because there are cow pies in or adjacent to the stream fertilizing the stream. If you select any 3 of these 5 subclassification items, it will trigger the conclusion to say that the range conditions suggest that livestock is compromising water quality. If you have more, it still has the same result in the conclusions. If you only have 2 items present on your site, it will not conclude a range disturbance at your site. The point of this tab is to capture potential for fecal contamination not related to fine sediment. Okay, so now let's have a look at the summary tab. The summary tab pulls all the results together on the same page. It gives you total fine sediment from surface erosion, which you can see is 0.5 cubic meters, total fine sediment from mass wasting, which is 0.2 cubic meters, and the grand total fine sediment, which is 0.7 cubic meters. Total coarse sediment generated is 0.8, and which is not important from the point of view of water quality, but can be very important for the fisheries downstream and from the fisheries management point of view. The coarse sediment may be of sufficient size that the stream channel can't be cleared and pools become infilled. When the pools become infilled, there is less surface water for the fish to live in, and in some cases, stream beds can be dry, with water flowing underneath through this coarse material and no room whatsoever for the fish. The coarse sediment value is anticipating that someone may be using this for evaluating fisheries impact, not related to drinking water. Just to remind you, only mass failures can bring coarse materials into the stream. Otherwise, when we are talking about fine sediment generation, we are talking about suspended material carried in water. The app translates the rating for FREP evaluations. In this example, it is low, which is dependent on how much fine sediment is generated. Anything between 1 and 5 cubic meters is considered moderate. The severity of ill effect on fish is taken directly from the stream characteristics tab previously discussed. On the right-hand side at the top, we can see that total impervious area contributing to the stream at site, which shows 250 square meters. This means for this specific site, that is the surface area that is generating surface water, which will all in turn reach the creek in a storm event. In other words, before the road was built, before the site was disturbed, that water would have stayed on site and trickled slowly through the subsoil. But now, because of the disturbance in the landscape, that water is intercepted and immediately flows directly into the creek. This impacts peak flows. This is more useful than just saying how much impervious surface area, like how much road surface there is in a watershed. This analysis determines not only how much impervious surface there is, but also the degree of connectivity to the creek. You can have a section of road that is impervious, but if the water from that goes off the road into the forest floor and gets reabsorbed, then it doesn't impact peak flow. If you find your site generates a substantial amount of fine sediment, Module 3, the icon up on the right, presents information about management implications. Open that up for you. You can go through that and have a look in your own time. It outlines management techniques related to layout, design, construction, management, through to deactivation of the site. When you do find that you have a site with greater than 1 cubic meters of fine sediment generated, there is a checklist of possible solutions to reduce fine sediment generation. These have been divided into sub-tabs of the life cycle of the road. In each case, there are different options for improvement that can be chosen. For example, you may have found that grader berms were an issue on your site. You would go into your management sub-tab down here and click on remove grader berms, number 16. Had someone paid attention to grader berms at that site, then the amount of fine sediment generation would be lower there. Conversely, if you maybe trained your grader operator to not leave those kind of berms, it would improve the water quality situation in the future. Now, there may be a situation where this checklist does not cover the issue associated with the site. In this case, go to the Other tab and click on Other Recommendations. This is going to bring you over to the Comments tab. Let's do that. So you see we're in the last tab up on the top, the Comments tab. And under the Comments tab, you could write whatever suggestions or observations you have. In this case, maybe it's to keep off the road during spring melt. Heavy machinery on poor road surfaces may cause unprecedented damage if the road is saturated. In the right-hand box, you have different options to add a picture directly from your iPad's camera or from saved pictures in the iPad. And the signature function allows you to do a fairly detailed drawing. Let's just do a signature. And you can do your drawing. Maybe you want to do a little diagram of your site or something like that. And that will be saved into the app. So the FREP WQE app is a useful tool to help a watershed evaluator collect and organize information crucial for better watershed management. For further information, the viewer can visit the Forest and Range Evaluation website. Thanks for listening.